Hello students, we're continuing our lecture on the nerve physiology and how neurons work. This particular segment is about the resting membrane potential, or the resting voltage of a neuron. When neurons are at rest, they have an electrical charge. And that's the key thing about neurons, is they have an electrical charge, and because they have an electrical charge, they are then able to transmit electrical impulses. And that's the action potential, that's the graded potential, those EPSPs, IPSPs. In this case right now, we're going to start by really focusing on that action potential. We're going to be focusing on the electrical impulse that travels down the axon, because that is the electrical transmission in a neuron. And for a neuron to do that, it has to have an electrical charge. And for a neuron, its electrical charge at rest is approximately minus 70 millivolts. Okay. And the voltage, that resting membrane potential, that voltage, is created by a separation of charges. Think about a battery for a minute. A battery has a positive and negative end, and that battery has a voltage. The reason that battery has a voltage is because of this separation of charge. Think about two magnets. If I hold two magnets apart from each other, I hold their positive and negative ends apart from each other. Those positive and negative ends of that magnet, they're going to want to attract and pull together and join. And in order to pull the positive and negative ends of a magnet, if I have two magnets, one positive, one negative end, in order to separate those magnets, I have to use force to pull them apart. And that force of separating that positive and negative charges, that force is energy, and that force is actually voltage. So the separation of charges, I create a voltage. What we're going to find in the neuron is that we create that separation of charges by having a membrane and by having different concentrations of two ions, in particular sodium and potassium. And it will be the separation, it will be the difference in the sodium and potassium concentrations across the membrane that will ultimately give us a separation of charges. If we take a look at it here, here's a neuron, and in this neuron we have placed a microelectrode. And so we've blown this area up, we have a microelectrode in place, and we can see that the interior of the neuron, just inside the membrane, has a negative charge compared to the outside of the neuron that has a positive charge. And this separation of charges across this membrane, that gives us a voltage. And we can measure that voltage, and in the average neuron, that voltage is approximately minus 70 millivolts. So again, this is at rest, and a neuron at rest, it's electrically charged because of the separation of charges, and we can measure that voltage, and that voltage is minus 70 millivolts. Now, how do we create that how do we create that difference in charges? It's due to a difference in the sodium and the potassium concentrations. In this case, in the extracellular fluid outside of the cell, sodium is very high, and in the interior of the cell, potassium is very high. And so then, at the same time, to create that difference in the sodium-potassium concentrations, we have this differential permeability of the membrane, where the membrane is slightly permeable to sodium, and this is through leakage channels, leaky channels that are constantly leaking, and then it's only slightly permeable to sodium, and sodium moves in a very slow level. But for the potassium, the membrane also through these leaky channels, these leakage channels, the membrane is very permeable to potassium, and potassium is always leaking out. Okay. And so then ultimately, because of those differences in the permeability of sodium and potassium, and because of the differences in the concentrations of sodium and potassium, we end up with the interior of the neuron slightly negative compared to the outside. And then we have one more factor to put in here, and this is something called the sodium-potassium ATPase pump. And this is a pump that ends up stabilizing that resting membrane potential because it helps to maintain the different concentration gradients of sodium and potassium, maintaining a high level of sodium outside and a low level of potassium inside. So let's put all that together here. In this figure, we're showing up here first. Here we have a high concentration of sodium outside, a low concentration of sodium inside. Opposite that, we have a high potassium concentration inside and a low potassium concentration outside. And then here is this pump And this pump is constantly pumping 3 sodium ions out for 2 potassium ions in. So if we were to separate each of these little components, if we just were to look at the potassium, with all the potassium constantly moving out, that would end up giving us a resting membrane potential of around minus 90 millivolts. However, we have a few sodiums always moving in, and that sodium moving in with the potassium moving out, that gives us this resting membrane potential of minus 70 millivolts. And finally, that's all maintained because we have this pump here, and the pump is moving 3 sodiums out for 2 potassiums in. That will maintain the high level of potassium inside the cell versus the high level of sodium outside the cell. And altogether, by creating that high sodium outside, the high potassium inside, we create a separation of charges, and we create an electrical charge in that neuron. And again, we can measure that electrical charge in the neuron. It's usually approximately around minus 70 millivolts. Thank you.